Let's do one last example of calculating a derivative by the difference quotient. I'll speed this one up a little bit because I've been pretty detailed in the last two. So again, to find the derivative, we could always start with the limit as h approaches 0 of f of x plus h minus f of x divided by h. And in this case, f of x is the reciprocal function 1 over x. So if we plug in x plus h into that, that would just be 1 over x plus h minus the original function, all divided by h. And here, again, I would recommend simplifying the numerator first. Remember the rule of thumb for dealing with rational functions, or when we have fractions with our polynomials, remember that in order to add or subtract them, you need a common denominator. And since these two objects have different denominators, the easiest way to find what we call the GCD, the greatest common denominator here, is to multiply them together, assuming they don't share. These two denominators don't share any factors. And remember, you can't just add h. That doesn't work. That's not a thing with fractions. We have to always use multiplication in order to produce equivalent fractions. But basically, we can multiply these denominators by each other, or not by each other, but by the respective other denominator. So the first denominator here, I'm going to multiply this through by x. So that would leave me with x over x times x plus h. And in the second fraction, I could multiply this by the other denominator, x plus h. So I'd multiply the numerator by x plus h. And the denominator, again, would be the same, x times x plus h. So we create a GCD by multiplying each one by the respective denominator. And now that we have a common denominator, remember the rule for fractions like this is we add across the top, the denominator stays the same. So I'll go ahead and move on to the next line down here. So what I'd be left with is x minus x plus h. And remember, just like before, you could always imagine that there are parentheses around the numerator, just, as I recommended in this case. When you're taking away a function, we need to make sure we're taking away the whole thing, because this was originally 1 over x, and this is equivalent to 1 over x. And when we're taking this away, we need to make sure that this negative gets distributed. So what I would have here is x minus h. X minus x will cancel, and what I'll be left with is simply minus h. So I'll have minus h divided by x times x plus h. Remember, the denominator, once it is common, you add across the top or subtract across the top, and the denominator is the same. And again, all of this is over h below. This is what we often call a complex fraction, which is basically the next thing that might get some students a little bit stuck here is, okay, what am I dividing? There's too many fraction bars. But remember, this fraction bar is technically larger, so it implies that I'm taking this divided by this. And a rule for dividing by fractions, it can always be helpful to remember, well, I could use the flip and multiply rule. If I'm trying to divide, if I rewrite the denominator as a fraction, h over 1, really that's going to flip over and multiply. And, I recommend using that when you're dealing with fractions in the numerator of the difference quotient, because it's already, kind of bad enough. But that would leave me with negative h divided by x times x plus h. And this would all be multiplied by, not by h over 1, by 1 over h. Because, again, in order to divide by a fraction, I can flip it over and multiply. Another basic property of how fractions work. And now you can see that I have a common factor, because now what I would have is, when I'm multiplying fractions, top times top, and then bottom times bottom. So this would just be negative h divided by x times x plus h times h. Or we could use the cross cancellation rule, because h divided by h will make 1, and that will cancel out. So what I will be left with here is the limit as h approaches 0 of negative 1 is all that's going to be left on top, and then x times x plus h on bottom. Now at this point, I could multiply out my denominator, or I could actually solve my limit, because the limit is, again, as soon as I cancel out this division by h, now the limit would work. I can plug in 0 because this rational function is no longer undefined at 0. So now if I plug in 0 into this, I would be left with negative 1 divided by x times x plus 0, or x times x, which is, of course, x squared. And this leaves me with my derivative function for this example. example. So in summation, the derivative of the reciprocal function 1 over x is equal to negative 1 over x squared. And again, we could use this function to find the slope of the tangent line at various points. In the next videos, we will look at actually finding tangent line equations. Basically, the gist of that is you want to start with the point slope form of an equation, find the derivative, and use it to determine its equation.